And I'd like to thank the organizers for inviting me to give a talk. It's a great pleasure to be in Korea. So this is, you could see that the date is off, but I'll pretend that this is when the talk was prepared. Let's see. What I'm talking about is joint work with Yael Karshon. And we have something written up and posted. So there have been a number of talks about things I'm going to talk about. So in some sense, this is going to be providing background for the talks that happened yesterday. So I'm going to start with a symplectic manifold, with a symplectic form. I'm not sure why I felt compelled to point out that it's non-degenerate and closed, but at this point of the conference. And as Urs explained yesterday, for any function, there is a vector field if you have a symplectic manifold. And then that vector field has a flow. And periodic flows came up. Well, Urs was talking about periodic orbits. I'm just going to save myself a lot of trouble by assuming that all the orbits are periodic. So I'm assuming that the flow is periodic. So it has period 1. And then I want to think about it as a group action, right? And my convention is that a circle is R over Z, so 2 pi is 1. And so whenever you have a periodic Hamiltonian, you have a circle action. Now suppose you have a bunch of these functions, and all their flows commute. So you can put these functions together into one map. It's called the moment map, and it, I guess, showed up yesterday, if not before. And it showed up in Dan's talk. I guess I could have just said, look, as Dan said in the first lecture, suppose we have a moment map. And so this map encodes an action of a torus in this way. Right? You just take the flows and you first apply one, then the other, then the next one, then the next one. And for the purposes of the talk, we could just say this is a Hamiltonian torus action. Right? It comes from Hamiltonians. As Urs explained, Hamiltonian is symplectic geometry speak for a function. We have no functions that are not Hamiltonian. All right. Now let me define toric manifolds, which showed up in Cho's talk yesterday, Professor Cho. So the condition that one wants is that the number of functions is half the dimension of the manifold, and they're independent. Right? This is the standard condition for the. So almost all values of the map are regular values. Another way of thinking about it that I have an effective torus action. So let me mention a few facts about toric manifolds. So mu is the moment map. Maybe I should write it here. So you have a symplectic manifold, toric. There's a moment map goes to Rn. A typical fiber is just a copy of the torus. So the fact that the orbits sit inside is not so deep, but dimension count forces the, well, I wrote it as a fibration. I guess I should just take some point here. So a typical fiber, maybe even more accurately, is what I'm trying to say on the slides. Okay. So another calculation coming from the fact that my Hamiltonian, the flows of the Hamiltonians commute is that the form vanishes in the orbit, on all the orbits. So they are isotropic. And then if you do a dimension count, you'll see that generically the orbits are Lagrangian. In other words, they are maximally isotropic. The biggest dimension you could have for the symplectic form to vanish. And so symplectic topologists get excited when they get Lagrangian submanifolds, and then they try to figure out if they can move them around by Hamiltonian flows, which is what Professor Cho was talking about yesterday. Now, if you have a Hamiltonian torus action on a compact connected manifold, then there are some results. I hesitate to call them classical, because the people who proved them are alive and well. But the moment maps for Hamiltonian torus actions, not necessarily for the ones of, so I should say, this is for toric. And now I'm switching gears in general. So this is toric, and is 1/2 dimension of the manifold. But what I want to do is switch back to just commuting circle actions, commuting Hamiltonian flows, where this condition does not necessarily hold. For example, you could have just one circle action, or on a 6-dimensional manifold, or a 2 torus action on a 10-dimensional manifold. So these moment maps have rather remarkable properties. So it's a theorem proved by Atiyah and Gilman and Sternberg that if you have a Hamiltonian action of a torus, so I'm supposed to be polite and use the pointer. So these symbols stand for manifold form moment map. So if an action of a K torus of some dimension, then first of all you have polytopes showing up, which are not necessarily simple. They're polytopes, they're rational. And this property people often refer to as convexity of the moment map. But what they mean is convexity of the image. And let me also emphasize this is for compact and connected. Right? Connectedness is sort of necessary because if you have 2 of these polytopes, one for each connected component, you can overlap them and you can get all sorts of strange things. Right? The image won't be a single polytope. And the other property that's less well known is that the fibers are connected. And it's not true for arbitrary completely integrable systems. Somehow it comes from the fact that you have an action of a compact Lie group. Now, so this is a theorem from early 80s, maybe 81, 82. And then there was a young mathematician, French mathematician Duzon, who decided to look at the toric case, complete integrability. And in this case, the results are even more rigid. So let's start with a compact connected symplectic toric and manifold. Then it's known that the image of the moment map is not an arbitrary polytope. It's unimodular. And because Duzon was the first one that symplectic geometers learned this word from, they started calling them Duzon polytopes. But I think unimodular polytopes have been around way before Duzon. And they show up for other things. So I'll stick to unimodular even though it's not the most popular choice in the literature. So the first claim is that the image of the moment map is a special kind of polytope. And conversely, any such polytope, any such polytope can occur as the image of the moment map, and up to isomorphism, it uniquely determines everything. The manifold, the symplectic form, the action. Right, so the next comment is, what does it mean to be unimodular? And that was referred to yesterday. So I'll draw a picture again. Right, so the condition you're looking at, so you have Rn. Inside Rn, you have a lattice of integral points. You have some polytope. Okay. Thank you. And the slide is still visible, right?
Yeah, it's visible.
Right. So you're looking at one vertex, and you're looking at the edges coming out. And the condition you want, so V1, V2. So you look at the vector spanning the edges, and the condition you want, Vn. And this n is exactly the same as this n. Right? So it's one condition of unimodularity. And what you want is that the vectors span z to the n over z. Right? And my abilities to prepare these slides are fairly limited, so my examples look like a list as opposed to a picture. So I figured I'll draw the picture. So here are the two pictures. Let's see. So the standard example one sees first is here's one, here's one. Here's a unimodular polytope. And you can check that this vector and this vector are in fact the basis of the standard lattice. The next example, if I go up one, is there color? I don't see color chalk. Well, I'll just draw another picture. Right, so. So this one is not unimodular. Thank you. So these pictures showed up in yesterday afternoon session. So I'm just copying them. Sorry? Right. So part of the content of Dozon's theorem is that if you see a polytope like this, you know there is a symplectic toric manifold. The image of the moment map would look like this. And if you see a polytope like this, there isn't one. Well, just there are different ways of saying what corresponds to this. And there's a different theorem that says that you can find an orbifold whose image will be this. Or you could say there is a torus action, but it's not toric. This can happen. Right? So if somebody draws a picture like this and they don't tell you that they're dealing with tori, or in the toric case, it doesn't tell you much. Is that okay? So in the toric case, you could only have polytopes like this and not like this. Not allowed. Right. And the point is that these two vectors are not a basis. Now I want to make a couple of comments about Dozon's theorem. It has two parts. So this is something I already said, that it has existence part. Given a polytope, there is a corresponding symplectic toric manifold. And that's probably the more interesting part. Well, I'm not sure which part is more interesting. They've been with us for almost 30 years, 25 years. People got used to them. But may have been shocking when it happened. So this theorem is the beginning of symplectic toric geometry. Sorry? So M is smooth. Everything is smooth. No singularities. There are singularities in the torus action. There are fixed points. The vertices are images of the fixed points under the moment map. And then there is a uniqueness result that says if you have that's another remarkable result. So I want to draw a picture. So suppose you have two toric manifolds, M1 and M2, and one polytope. And you have two moment maps. And suppose you know that their image is exactly the same. So this sits inside Rn. And I'm deliberately confusing the issue whether this is a delta or a polytope. And the claim of the theorem is that there exists an isomorphism. Right? So by an isomorphism in the category of symplectic toric manifolds with moment maps. So there is an equivariant map that preserves the intertwines this, pulls one symplectic form back to the other, and intertwines the moment maps. Another thing I want to point out that Delson's theorem uses heavily the machinery that Atiyah, Gilman, and Sternberg had to develop to prove their convexity and connectedness results. And if you look under the hood of the Atiyah proof or of Atiyah's proof or Gilman and Sternberg's proof, it's Morse theory, really Morse-Bott theory. And the statement that's key is that if you have a periodic Hamiltonian, then it's a Morse-Bott function, and all the indices are even. That's what makes the whole thing work. Right, so if you like, here's a proof of the Atiyah, Gilman, Sternberg convexity theorem. Well, compressed or short sentence. Now, what I want to talk about is what happens if you throw caution to the wind. Namely, suppose you say, okay, I don't want compact. What's true in general? Well, it doesn't look like anything is true in general. You lose Morse theory because you don't even, well, something that I think Urs hit yesterday in his talk, one of the bold things that Floer did was he said, I don't have not only did Floer not have compactness, right, the space of loops is not compact, he didn't even have a flow. He only had flow lines connecting the critical points. But anyway, there is no Morse theory in a non-compact setting in this case, because we're just taking take a compact symplectic toric manifold and remove arbitrary subsets. You won't even have flow lines. The second thing you notice that the fibers of the moment map need not be connected. And then the image is a mess. It's pretty much arbitrary and doesn't tell you anything. Once you know that the fibers are not connected, so the cheapest example of constructing something with a strange image is, well, you have the cotangent bundle of your torus, which is Tn cross Rn. You have a projection onto Rn. Now take any manifold you like and take an embedding, local embedding. Local, maybe I'm not saying it right. What I really want to say is a tau map. So this is a manifold of dimension n. So this is a local diffeo. Well, then you can think of it as a principal torus bundle. Has a symplectic form on it. You could pull it back. That's a perfectly good symplectic toric manifold again. And here's the moment map. So if this is, you could take a piece of, you can take a disk, open disk, and wrap it around any which way you want. Well, maybe you have to have some, sorry, this would have full singularities, so you do something. Maybe you could do this. And so that's a typical image of a moment map that you'll get. And what does it tell you? Did you know that you started out with a disk cross T2? You didn't. There's no way to tell. And if you can get an annulus, open annulus. Right? Questions? So, thank you. So this is where I wanted to do this about sometime last century, and I was pretty much stuck. And what we needed to do was, well, think. So the first observation is one shouldn't be obsessed too much with the image of the moment map, because in Dozon's case, you can't tell the difference between the image of the moment map and the orbit space, because the fibers of the moment map are exactly orbits. But if you look at the orbit space, it's still a manifold with corners. And then you could sort of, this picture, I drew this picture for a reason. So what happens in general? You start with some symplectic toric manifold in the moment map. You can pass to the orbit space. And the moment map will drop down because it's equivariant. So I'll call this orbital moment map. And so the question somehow reduces to, almost reduces to differential topology, but for manifolds with corners. So this orbital moment map is what I would like to call a unimodular local embedding, which is a very fancy way of saying that it's a local diffeomorphism from a manifold with corners to a. So my orbit space will have exactly dimension n. And I'm looking at local diffeomorphisms, but corners don't just go to arbitrary corners inside Rn, they go into unimodular cones. So the same condition as you had for the polytope. So here is your orbit space. I don't know, something like this. This may not be there. Might have code. And the embedding will take each of these corners and straighten it out. Into a nice, not just polyhedral corner, but the edges spanning it will have to be a z basis. And it's not hard to prove. So here's our theorem. And I'm not sure when I prepared the slides why I started with the hard part. So here's the counterpart of the existence theorem. So given one of these setups, given a unimodular local embedding, psi, given a manifold with corners, and unimodular local embedding, there exists something that gives you that embedding, that local embedding. And then there is uniqueness. And uniqueness is in quotation marks because you don't have uniqueness. What you have is a classification of all symplectic toric manifolds with a given unimodular local embedding. And so the manifolds are classified by this collection of cohomology classes. There's a bijection. Now, if you were taking notes, you could try and compare it with a statement of Dozon's theorem. And why did he have uniqueness and we have this junk? Well, the orbit space for in Dozon's case is a polytope. So all of this vanishes. So you just don't see it. On the other hand, if you take a polytope and delete a bunch of points or some closed subsets, you'll get something non-trivial. And you start getting these extra characteristic classes. And I think classes like that show up in classification of complete integrable systems. So in some sense, this is not completely new. So 2 comments. The uniqueness part is not hard. Or maybe the accurate statement is it was well known how to do it to about 4 or 5 people. So it's not unusual in mathematics where people working on something know how to do it, nobody writes it down. The existence part is much harder. Because, well, if you ever looked at how Dilzon, in the case of Dilzon's paper, if you read Dilzon's paper, you'll discover that he works much harder to prove uniqueness because he had to prove that certain cohomology vanishes. And the way he does this is by doing check cohomology computations by hand, which is hard. But the existence is easy in the compact case because given a polytope, there is a machine that you shove it into. And it spits out the symplectic toric manifold as a symplectic quotient construction. And you can program it in. A computer can do it. But in our case, so as I was saying a second ago, in the compact case, the existence is proved by an explicit symplectic reduction, symplectic quotient. And the necessary group actions are just read off the convex polytope. Well, in the non-compact case, there is no polytope. And there is no symplectic construction that I know of. In fact, another thing that can happen in a compact case, let me draw another image of the moment map, a possible image, could look like this. You could have a polyhedral set of an infinitely many vertices. So if you were trying to realize that the symplectic reduction would have to be infinite dimensional. I don't know if anybody has done it, but we didn't even try. So again, you need to do something. So the idea is, let's fix a unimodular local embedding, and let's just study the existence and uniqueness problem. Well, the existence problem for one fixed embedding. So I'm fixing this. So I'm going to erase this. So this goes into Rn. Here's psi, here's your W of dimension n. Now what I want to do next is stick a whole category over this W. So the objects of this category are going to be triples, manifold, symplectic manifold of dimension 2n, and I want them to be, I don't know if you can read this. So here's W. I want them to be sitting over W. Here's mu. And I want this to commute. So these are the objects of the category. So this is, so things are like this are objects of toric symplectic manifolds, and it's decorated with this map. So in the compact case, it's not terribly interesting category because you just look at all symplectic toric manifolds with a given polytope. Well, it's a boring category. It has lots of objects off the top of your head, and they're all isomorphic. Now, I've defined a category, but in mathematics, definitions are cheap because it's not clear there are actually any objects in this category. I mean, why? This is the existence part. So the existence theorem says that this category is non-empty. Why should it be non-empty? All right? Well, there is a category sort of floating around that people haven't really thought much about. Is it okay if I put it on the other side? And that one is definitely non-empty. So we have this manifold with corners. And I could just look at the principal torus bundle sitting over it. So here's W. So I can look, again, I'll fix it. You could see why it's not on the slide. I mean, here's my W. And then I want to look at principal Tn bundles. But I don't want to look just at any. So this is a bundle with corners. And I'll draw a couple of pictures. Well, here, I might as well do it now. So suppose your W is just an interval sitting inside R. So a typical principal circle bundle would be just a cylinder. So here's B. And it has a perfectly good symplectic form. Right? So if I call this variable r and this variable theta, I have dr wedge d theta. Nice smooth symplectic form. So I can look at symplectic. So this is TSB, B for bundles. And whenever you have a symplectic form, you have a moment map. I haven't quite seen moment maps and manifolds with corners, but what's there to stop us from defining them? So might as well. And it's easy to see that this category actually has objects. It's a little bit harder to see that it has products, but it does have objects. Right? How would you get an object of this category? Well, you have a trivial bundle sitting over Rn. Pull it back. The symplectic form pulls back too. The reason why the pullback of the two form to one of these bundles by a map like this is non-degenerate, it's clear it's closed, is because this is locally an embedding. Right, and this is the example that a typical object sitting over an interval on this side would be a cylinder, and a typical object sitting over an interval there would be just a two-sphere. Right? And if you ever gone to talks on toric manifolds or moment maps, this picture shows up all the time. So what we prove is that there exist an equivalence of categories. And this is where all the work goes into. So this is a slick way of saying that if you have one of these bundles with corners, you can collapse things over the boundary. So here I have circles sitting over the boundary. I can collapse them to points, and I'll get that picture. The claim is that you can do it smoothly and symplectically. Alternatively, you could start here and blow up the fixed points. Right? You have two fixed points, and you're doing real radial symplectic blow up. So that statement says that you can either blow things up, blow things down. The hard part is, if this is a matter of choice which direction you want to go first. Or, right, when you prove equivalence of categories, you need to write down the functor. You need to prove that it's full, faithful, and essentially surjective. So mucking around with blow-ups is a statement about objects. And you could try to prove that, or going down with this collapse, right? You have to prove that if you just take a manifold with corners and you start collapsing things over corners, you get something smooth. And that the symplectic form that's in the interior will extend over this blowdown locus. So that's where the work goes in. And the reason why it works is basically these pictures. Because the radial blowups replace Cn by torus bundle over a corner. And then you have to be sure, you have to be careful to show that this can be done naturally. So things I've been talking about. You trade fixed points for corners. It's a blow up, blow down. It also explains why you classify toric manifolds by these things, right? Because if you just look at this, this is classifying principal torus bundles. But I don't want just any principal torus bundle. I want one with a symplectic form. I have to keep track of the form. So the integral cohomology keeps track of the bundle, and the class in there keeps track of the form. I knew it was going to happen. Whenever I give a talk with these slides, I usually run through them at a breakneck speed. And I think I've done that today too, as you can see by that number. The category of bundles actually has multiplication. This is not completely obvious, but let me say what it is, what the multiplication is. So if you ever read Grothendieck, which I'm sure everyone in the audience would have every reason to read. Sorry, in which category? This one? So equivariant maps. Equivariant maps preserve in the symplectic form. Sorry? It's not quite a group because, well, I'm going to start putting, because multiplication is not associative. It's associative up to isomorphism. So here's what's going on. Suppose you have two bundles over a manifold. They're all T-on bundles. And I want to construct a new bundle out of these. What would you do? Well, you can take P1 cross P2, still sitting over W. But that's a principal T-on cross T-on bundle. There are too many torus actions, so you kill one. So this is the multiplication. And then if you're extra especially careful, you notice that P1 cross trivial bundle, well, times trivial bundle, it's not equal to the trivial bundle, it's isomorphic. Sorry, it's not equal to P1, it's isomorphic. So there's canonical isomorphism. Then you notice that P1 times P2 times P3, well, it's not quite equal to P1 times P2, but it's canonically isomorphic. So this is what I mean by categorified. And then you can prove that, well, if you do multiplication in the opposite order, it's not the same, but they're again isomorphic. So it's commutative in this sense. Equivariant maps. Oh, I don't see how to multiply them. They're just equivariant maps, right? So these are, well, if you like, phi P1 to P2, phi is equivariant, right? So this is the group. Sorry, this is the group without the symplectic forms floating around. Now I want to add the forms, right? So the objects in my category are these guys. So somehow I have to stick on a symplectic form on this. And the answer is, yes, you can do it, but what do you actually do? Well, you take P1 omega 1 cross P2 minus omega 2. You flip the form. And then you take a symplectic quotient at 0 by the Tn action. That's the multiplication. And I haven't seen it before. Now, why on earth am I talking about this funny thing? The category on that side is a torsa for this category. This group acts on the symplectic toric manifolds. And the action is simple transitive. It's just that this guy has a trivial bundle. It's not completely clear what a trivial symplectic toric manifold is. But there is an action like this. And the simple intransitive means that this map, this functor from here to here, is an equivalence of categories. So you could take one symplectic toric manifold and start twisting it by the torus bundles, and you keep getting new symplectic toric manifolds. In fact, you get all of them. And maybe I'll conclude here. Anything more? Nope. Thank you.